So this presentation is based on my experience with patch analysis for most patches coming from Microsoft over the last 12 months. But the presentation is not exactly about patch analysis. It's more about various tips and tricks about reverse engineering large commercial software such as Microsoft software. It has three parts, and the first part will talk about how to set up your reverse engineering environment so that you have access to all the different versions of the software that you want to reverse. And the second part, I'll talk about various features of the Microsoft binaries that are important when you're reversing them and you might not have seen if you have reversed other kinds of software. And in the third part, I will talk about the IDA auto-analysis algorithm and how to make it better. And specifically, I will talk about a symbol loading plugin that I wrote, and it improves the results of the auto-analysis significantly. So, a lot of you are probably familiar with reverse engineering, but most reverse engineering talks and information that I have seen focus on reverse engineering malware, probably because there's a lot of malware to reverse. But when you're reversing a commercial application, you have slightly different challenges. For example, most Microsoft files are much, much bigger. The IE rendering engine in MS-HTML DLL is more than 3 megabytes. It is also heavily object-oriented code. It uses a lot of COM components. RPC interfaces are also very common. So you have to understand all these things. And when dealing with viruses, I guess you don't see those things very often. Also, one difference is that everything is compiled with the same compiler, which helps a lot because when you see some kind of features in one DLL, you know that you can apply them to all other files in the same release of the operating system. So when I first started working on the patch analysis, I realized that to do it properly, I need to have all versions of the Microsoft software. So I started on this by downloading all of it from our MSDN subscription. These things are great, by the way, because you can get almost everything that's ever been released, including 16-bit Windows. So downloading those was easy because it's not that much stuff. Downloading the security updates is a little bit harder. For patch analysis specifically, you need the security updates because when you do a diff, you want to diff the current patch against the last released version of the DLL, which is most often the last patch that patched this component. So to download those, I have some scripts that use the MS-Secure XML file, which is used by the Microsoft Baseline Security Analyzer. And this XML file is available from a special URL on the Microsoft website, and it contains all security bulletins that they've released, information about them, the list of files that have changed, and direct links to the downloads. Unfortunately, my scripts don't work anymore because they stopped updating this file with the release of NDSA 2.0, which uses a different format. But since I already have all these old security updates, the only new security updates I need to get are once a month, just a couple of files. So those you can download manually. Once you have the updates, you have to extract them. Now the updates are usually in some kind of compressed format, usually a self-extracting executable. There is this little utility called CAP-extract, which can extract the most common archival format that Microsoft uses. And the great thing about it is that it works on Linux too. So you can just run this and you can extract most security updates with it. Some Microsoft software, Office, for example, uses these MSI files, which are a little bit trickier to extract because the MSI files usually contain a CAP archive, which you can unpack with CAP-extract utility, but very often the files in that archive would have Mango names. because MSI has a lot of features for scripting, so very often the installation system would install, it would use the mangled files, and when it unpacks them, it would rename them and put them in the proper places in the system. So, and very often this is computed dynamically during the installation, so very often you don't really know, like you would have the data for some file, but you don't really know exactly which file this is and where it goes. And I still haven't found a very good solution for this problem. What I do currently for Office software is to just do an administrative installation, which basically extracts all the files and puts them in a directory. And from that directory, you have all the unpacked files, so you can deal with them. The problem there is that when you install a security update, you have to copy your administrative installation, which is multiple gigabytes, apply the update, then div the contents of the two directories to find which files have been updated, and just extract those files. So it just takes a lot of effort to do something that should have been simpler. The main reason for the problems with the MSI files is that they have very sophisticated scripting support, and a lot of the scripts in them are dependent on what software was used to produce them. For example, install shield MSI files would look very different than files produced by some other installer. Some other complications I ran into. Some of the files, even in Windows 2000, are renamed during the setup. So if you look at the files in the installation CD, they're going to have different names than the files installed in the system. The SMTP SVC DLL is one example of that. And also, recent Microsoft patches use some kind of an additional compression. So even when you extract them with cam extract, you just get a bunch of files with weird names. And to get the real files out, the only way to do that is to actually run the update with the /x option, which tells it to unpack itself. The problem there is that, unfortunately, you can't do it on Linux. You would need a real Windows machine to run it on. And you should make sure that you got the update from Microsoft and not from somewhere else before you run it. So once I get all these files extracted, I add them to a database of DLLs, which I call the DLL database. Although the name is not very accurate because not all of the files there are DLLs. A P database would probably be more accurate. I store the file, and I also store the following metadata about each file: name, size, modification date, hash, the path to these symbols, and a textual description of where the file came from. So, for example, this file came from Windows XP, Service Pack 1, the 0307 update, and the QFP build. And for those of you who don't know, recent Microsoft OS have had these two builds that they do, QFP and GDR. And QFP is basically their software plus various compatibility fixes and other improvements they've added on, not necessarily security related. And GDR is their build environment that contains only the basic software. So if you're working on doing some kind of diff, it's important to diff a GDR file with a GDR file instead of mixing them together, because then you'll get a lot of extra changes. Right now my database is more than 30 gigs of files, 7,500 different file names, 28,000 files total, and it's getting bigger every time. And this doesn't even include Office. This is what the DLL database looks like when you actually use it. I have this tool for checking out files from the database, and when you check them out, it builds here I ran the checkout command, and I told it to get me NTDLL DLL. So it copied out all the versions of NTDLL and it put them in these directories, and the name of each directory is a textual representation of where the file came from. And I also put the file version in front so that Windows Explorer sorts them correctly. So now if you want to diff the file from MS0307, you can very easily see which is the last release of NTDLL to diff against. Symbols are another thing that's very useful to have. Microsoft provides debugging symbols for most of their stuff. Unfortunately, not everything. For example, Office does not have debugging symbols for any Office releases. With other software like Exchange, for Exchange 2003, they have symbols only for Service 2. So if you're reversing something from earlier releases, you don't get symbols. And what I do there is I use bindiff to compare. If I'm reversing Service Pack 1, I would compare Service Pack 1 against Service Pack 2. And then for all the functions in bindiff matches, I would import all the names from the file that I have symbols for to the file that doesn't have symbols. The good news is most of the core Windows stuff has symbols with very few exceptions. There are a couple of security updates that for some reason they just build without symbols, or maybe they just didn't upload the symbols. But these are exceptions rather than rules. For example, for MS-HTML, which has about 100 different versions that have been released so far, I think there are only 4 or 5 that I don't have symbols for. Everything else comes with symbols. So once you have all these things set up, you can start reversing. And here are the things that you're going to see very often when you reverse Microsoft software. The first thing that you're going to see is function chunking. Function chunking is appeared relatively recently, and until version 4.7, IDA had a lot of trouble dealing with it. Basically, what this optimization does is it takes the function and it splits it into multiple chunks of code, which are then laid out in different places in the file. So instead of having one contiguous area of code that corresponds to the function code, you would have a little bit here, and then a little bit down here, and then a lot of other stuff in between. I believe that the reasons for this optimization is to take error handling code and other code that's not executed very often and put it at the end of the file so that the pages that are being executed, that contain the code that's executed more often, stay in the physical memory. But the error handling code can actually get swapped out without hurting the performance because it's rarely executed. One benefit that this gives us, the reversers, is it tells us which code is likely to get executed and which code is not. So we can use this profiling information, which was used to do the function chunking, and we can extract the profiling information back from function chunking. And here's an example of that. So here we have a function which is pretty small, but if you actually look at where this jump goes, the jump goes way out of the function. And if you follow it, you see this function chunk here. And the function chunk is, if you look at the addresses, the function chunk is just located at a very different place. And this function chunk deals with error handling. It says the last error. So if you're reversing this function, you can know that the regular execution path is right here from top to bottom, and it does not involve the error handling code. Now, in this case, you could easily guess that, oh, this is error handling code just by looking at it, but in some cases, it's more complicated. So knowing that the function chunk goes off to some other place might help you figure out that this is maybe not code that you want to look at. If you're trying to figure out what the function does, then you don't want to look at the error handling code. But if you're looking for vulnerabilities, maybe the error handling code is exactly the place where you want to look at, because it's rarely executed. It deals with boundary conditions, and it might not have been tested as well as the main execution path. Another weird thing that I've seen is function fall through. And the compiler there, if you have a function which basically acts as a wrapper around another function, the compiler can put the two functions right next to each other, and then instead of having a call, it will just have the first function fall through to the second one. And here's an example of that. So here we have the URL cache commit file function, which does a call to init globals, and then if that returns 0, the function will return 2EE4, and then here we have the return instruction of the function. But if it's not 0, then we'll just fall through all the end of the function into the next function, which is add URL. So the actual C code of the function probably looks something like this: checking it globals, and then if it's not 0, then we call this other function. And this thing completely wrecks the IDA auto-analysis sometimes, because IDA just assumes that if IDA sees the first function first, it'll just create that whole range as one single function instead of two separate ones. So this is something to keep in mind. Here's another optimization which is very, very evil. It is kind of complicated, but it works like this. If you have an array reference, and let's say EAX is your index, and you want to reference A of EAX minus 1, that's very common if your array starts from 0 and or EAX starts from 1. If the compiler knows that EAX is guaranteed to be greater than 1 by doing constant propagation, value range propagation, then instead of having the first code which decrements EAX and then uses it as an index, it will just generate, it will skip the decrement instruction, and it will just generate the second line of code there, which uses an array base of B, which is 8 minus 4. So this is kind of hard to explain, but maybe an example will help. Here we have this array, and you can see that the array contains offsets of strings that start right here. Obviously, this is where the array starts, because the previous element is not a valid string offset. But for some reason, I decided that there is a reference to the previous 4 bytes. So what happened here is we had a reference, the array starts at this address, and we had a reference to it, and the reference was using something like EX minus 1. So instead of doing the decrement, the compiler just used this address as the base. And because EAX is guaranteed to be at least 1, then the first element, which is not a real element, will never be accessed. We'll always do the access from the second element. And this creates a problem. The problem is that this function here, by the name, you can tell that it's obviously a function. But I did not create it as a function. If we try to create it manually, it says the function has undefined instruction data to this point. And if you look at that address, which is B7, that address is right here. So at the end of the function, we had a leave instruction, which should be followed by a return instruction. But instead of the return instruction, we had this undefined data. Why did this happen? This happened because the return instruction is 2 bytes long. The second byte is right here. So if we convert this to code manually, the return instruction appears. So what happened is I just saw the reference to the second byte of the return instruction as a data reference first, created the data item there, and then when it was tracing the code, after the leave instruction, it hit the data, and it didn't know what to do. So this is something pretty complicated to actually get right in an analysis algorithm, because how are you going to know that your array reference is not, that the array doesn't really start there? So this is just something that I've been looking for manually and fixing manually, but you had to know that it exists so that you can recognize it when you see it. The other optimization, which doesn't matter so much for reversing, but when you're debugging, it can be a pain in the ass, is the reuse of stack frame slots. Now, if you compile without optimizations, each local variable, each argument would have its own slot on the stack. And then when you use it, when you see a reference to this place on the stack, you know that, oh, this is this variable, and the correspondence is 1-to-1. But if you're compiling with optimizations, then the compiler will calculate the length ranges for each variable. And if it sees that a variable is not needed after a certain point, it can just reuse the same stack slot for some other variable, which saves memory at runtime. So, for example, in this little function, we have a call of a member function of an object, and the object argument is only used in the call. After the call returns, the object variable is never used again. So where would the compiler put the A variable? Well, since it knows that the argument slot is not needed after the call, it will put both the object argument and the A local variable in the same argument slot. So sometimes when you're doing reversing, you will see, so here we have the arg4 variable and the arg4 argument. So here we use the arg4 argument, and then if we scroll down, we assign to it, and then we use it again. Now obviously the second time when we use it, we're using the value that was assigned up there instead of the actual argument value that was passed. So unless you know who assigned to this variable, you don't really know if you're using an argument or if you're using something else. So you can't just tell what something is by looking at its name. Just because you've seen arg4 earlier in the code doesn't mean that the arg4 here is actually the same variable. The next optimization, which is actually fairly common, is a comparison optimization using the SVB instruction. This instruction normally counts its second operand in the carry flag, and then it subtracts it from the first. So if you have SVB with EAX and EBX as arguments, then the result is EAX minus EBX equals the carry flag. But in the SVB comparison optimization, the compiler generates SVB with the same register as both arguments. And this is EX minus EX equals the carry flag, which is equivalent to EAX is the negative of the carry flag. And here's an example of what this optimization, what this pattern looks like. You would have a comparison instruction first between two registers, and then on the right you can see the two columns show the values for the two cases, EBX less than ECX or greater than. So if it's less than, the carry flag will be 1, otherwise it will be 0. That's set by the comparison instruction. Then when we do the SVB, the negative of the carry flag is assigned to EAX, so now it's -1 or 0. Then we increment, so now EAX is 0 or 1, which corresponds to false or true in C. So the actual C code is, if EBX is greater than or equal to ECX, then return 1, otherwise return 0. And sometimes it gets even more complicated than that. For example, my screen is not wide enough. Okay, well that's as wide as it gets. So for example here, we take this global variable dehibernating, which is obviously a Boolean variable, so it's 0 or 1. We assign it to EAX. Then the make instruction sets the carry flag to 0 if B hibernating is 0, otherwise to 1. The SBB instruction assigns the negative of the carry flag to EAX, so now EAX is 0 or minus 1. Then we end EAX with this value, and the result is if B hibernating is 0, then EAX will be 0, otherwise it will be A0E or minus 0. After that, we add to it. So now, if hibernating is 0, then EAX will be 7530, otherwise it will be A0E something something something. So when you reverse this kind of code, you can convert it to the following single line C instruction. If B hibernating is true, then return A0E BB00, otherwise return 7530. So this is not very hard to do manually if you know what the SUT instruction does. And this is a very common thing. I see it over and over again. Here's another thing which I've seen a couple of times. I'm not quite sure why it is there, but I've seen this code where you shift the register right by 10, then you test, and then jump. And shifting it right is equivalent to dividing by 65K, 64K. And then you check if the result of the division is 0, which is equivalent to checking if the higher 16 bits of the register are 0. I'm not sure if the compiler, I don't know why the compiler just didn't compare PCX with 64K. Maybe the shift in the test instruction takes advantage of some processor parallelism, so it works faster. Or maybe the programmer just wrote the code as if the register divided by 64K is 0, then go to that place. But I've seen this in a couple of different files that were unrelated, so I'm guessing that this is compiler optimization rather than the programmer just writing code like that. The next optimization which you'll commonly see is a switch optimization. If you compile with the 0 optimization flag, then this switch statement will just translate into a sequence of comparisons and then jumps, conditional jumps. But if you compile with optimizations, you end up with this. We would compare the argument, the range for the switch statement gets cut into 2 halves. And then we compare with the middle point, and we go off to, there's this place where we go off to if it's greater than 8001, and then this code is executed if it's less than. So instead of having one long sequence of comparisons and conditional jumps, now we split it into 2. So to get to the end, we only have to execute half that many instructions instead of going through all the comparisons. The other thing that you'll notice is that we don't actually do comparisons. We decrement EAX. So here we would decrement it once, and then we have a conditional jump to case 1. The conditional jump is 0. So if EAX is 0 after 1 decrement, this means that it started as 1, which means that this is case 1. Then we would do another decrement, and we have another jump at 0. So if EAX is 0 now, after 2 decrements, it means that it started out as 2. And sometimes instead of a simple dec, you would have a sub-instruction. So to find out which case a label corresponds to, you have to add up all the decrements, and you'll get the initial starting value that was required to take this statement. And I also have an example for that, which doesn't look very different from the slide. I have a jump to 2. this is case 0, then I do a decrement. Now we are in case 1 because we decremented the X one time. This IDB will be available on the website, so you can look at it in more detail later if you need to. Another thing, which is more of an IDA problem than a Microsoft thing, is the P files contain all these data directories, which are optional information that's in the P file. And these data directories, if you use dump bin to look at the headers of the P file, you'll see all the data directories. And for example, here with the export directory, it starts at this relevant address, and it's this long. Now, the trick here is that the compiler doesn't really put this data in some extra segment. It very often just dumps it into the text segment or the data segment or just somewhere in the file. So IDA doesn't recognize that this is not code or data because it sees something in the text segment. And if you look down here, see this is the address 1984, which is the address where the export directory starts. So this long array of numbers is actually the export directory, which contains a list of all the functions that are being exported. And as you can see, it's in the text segment. Then after that, we have this sequence of ASCII strings, which are not actually strings. They are the names of the functions that this DLL exports. So in this case, we were lucky because IDA just created this as an array of data, and it doesn't really interfere with the rest of the analysis. But sometimes IDA would, when analyzing these bytes, IDA would decide that, oh, this looks like a function. So you'll get a function there, and then this function might jump to some random places in the file, and this screws up your analysis. So it would be good if somebody writes a little plugin which parses the P file and then creates all these data directories as the proper structures that they're in, so you can see them in the file instead of having kind of trying to guess whether they're code or data or something else. I was going to talk about exception handling, but there was this article posted up on RC, which is so much better than what I was planning to say. It has nice graphs and everything else, so you should go read that. And there's also a little IDC script which creates exception handlers properly, so you should go look at that. I'll just give you a little example of what the exception handling looks like and why it creates a problem when analyzing the binary. So here we have this code which just sets the EX to 1 and returns. But as you can tell from the color, it is not part of the function. It's just some code that's sitting in the text section. If you look at the cross-reference, that the only cross-reference is the address of this place is in somewhere in the text segment. This thing is actually an exception handling record or scope table or something like that. It contains the offsets of all exception handlers for a specific function. And if you look at who references that, it is in the close my cert store function. And in the very beginning of the function, we push the offsets to that scope table, and then we call ACH crawloff. And ACH crawloff registers an exception handler and puts that scope table address there. So when an exception happens, it can be addressed. It will be looked up in this table, and then we'll jump to the right exception handler. The problem here is that since IDA doesn't know about the scope tables, it did not create. This should actually be a function chunk because this code is actually part of that function. But IDA didn't know about it, so you end up with some random code sitting in your text segment. I believe the IDC plugin that was linked up that article that I mentioned earlier actually does that. It would create a function chunk for that area of code. The last thing we're going to talk about is the Microsoft hop hashing. So Microsoft has this hop hashing implementation, which allows them to ship patches that are applied at runtime. And right now, this is only supported for Windows 2003 Service Pack 1. And it's only supported for some hop patches. I believe at this point there have only been maybe 5 patches that contain hop hashing support. So the hop hashing support is actually kind of interesting. The way it works is you have your running process. Microsoft ships this DLL with a hp.dll extension, and this DLL gets loaded into the running process. Let's say you're running Exchange. So this DLL will get loaded into Exchange. Then all the functions in Exchange are compiled. Actually, Exchange is not a good example because it's not part of 2003 Service Pack 1, but some other service. So all the functions in the DLLs of Service Pack 1 are compiled with the with a /hop hash option of the Visual Studio compiler. And you can actually use this option on your own code. And what this option does is it puts a move EDI instruction in the beginning of every function. So if you go there and look at it, in most functions you'll just see this move EDI. So this instruction obviously doesn't do anything. It's equivalent to a null. But they put it there because it's 2 bytes long. And if you want to modify, if you want to write to that function, you can override these 2 bytes safely, even on a multiprocessor system, because you know that there is no code that's, if you actually had 2 separate 1-byte instructions, and you had a multiprocessor system, you could have a case where one thread on one processor is executing, like it's right between the 2 instructions, and then you override the 2 instructions, and now that thread is in the middle of your stuff that you've overwritten, and it will execute some random code depending on what that byte is. So having the two byte null there allows you to override that with a short relative jump, which is exactly 2 bytes long. That relative jump would go 5 bytes earlier. It's basically jump minus 5. When you go 5 bytes earlier, you end up right here, where we have a sequence of 5 knobs this time. These 5 knobs would never get executed normally, they're just padding. But when you apply the hop hash, you would put a 5-byte absolute jump in that place that goes to your hop hash DLL. So this means that every time that function is executed, you'll do the short relative jump back here, then you'll do the 5-byte absolute jump to your hop hash DLL, and you'll end up executing code there instead of this function. So this gives them the ability to replace any function in their file with an updated version. Now this has a few drawbacks, this approach. One is you can only replace at a function level. If you want to do something at a deeper level inside a function, you can't. And the other drawback is that since you're replacing this whole function, you can't modify any data structures or classes that this function uses. It has to sort of fit into the rest of the application. So you're limited in what kind of things you can hop hash, which is why they've only had 5 patches that do hop hashing up to this point. I believe they also do it only for critical vulnerabilities, so they don't have to bother doing it for something that's not terribly important. But the obvious benefit is that you can apply it without having to restart your server. So, having gone over all these problems with IDA and all these optimizations to create problems, now let's look at how you can make things better. We'll start with the auto-analysis algorithm. Now, the algorithm is not actually documented. The best reference I think we have is the IDA SDK, which doesn't really tell you that much. And then there's this post on Ilpak's blog, which it actually happened as a result of this very slide, which I had at CanSec. And when Ilpak saw it, he said, yeah, you got the algorithm mostly right, but here's a little bit more detail about how it works. But very basically, the algorithm works like this. Once you load the binary for analysis, IDA finds all the entry points, which are the DLL entry point and then all the exported functions. And it adds these to the code analysis queue as potential functions. Then it goes through all the bytes of the file and it looks for the common function prologs, push EBP, PSP, stuff like that. Also the move EDI, EDI instruction, I believe they added that in the recent version of IDA. And when it finds these common prolog chunks, it says, oh, this looks like a function. So it also adds it to the analysis queue. Now we have all this stuff in the queue. We'll start iterating through the queue. We get an address, we start disassembling there. And as we do the disassembly, all jumps and all calls we also add to the queue as potential instructions. So basically, IDA covers all the code that is reachable from the entry points. Sometimes this doesn't really work if you have, for example, if you have a object-oriented program and you have virtual functions. These virtual functions will never be called directly. Instead, you would have a virtual table which contains the addresses of all these functions. And then the calls would be through the virtual table. So to deal with that, IDA would find all things that look like an offset into the data segment, and then it would create that as a 4-byte pointer, and then the things that it points to, it will try to guess if it's a function or not. And if it's a function, it will create code there. After it's done with all this, we have the final analysis pass, which goes through the database and all unexplored bytes, which are bytes that we haven't reached when we did the analysis. It applies heuristics and it tries to guess if they're data or code, and then it creates either data or code there. So the two main problems that you see, which are not really problems if you're doing manual analysis, like if you're going through the database and manually telling it, oh, this is code, this is data, that's not really an issue. But if you're doing automated analysis, such as preparing a database or diffing with BitDiff or running some other automated tool, you don't really want to have to do that manually. So it is very good to have correct results come out of the auto analysis. The two problems I've seen are data, which IDA disassembles as code sometimes, and also functions which are not detected as proper functions, or function chunks which are not detected properly. Here's a little example of what these auto analysis problems cause. This is the names window, which shows you all the strings, functions, other data, and you can see these two names there, which are disassembled as code, hence the C. But the first one, just by looking at the name, is obviously a string because it starts with SC, which is a string in the Hungarian notation. Then the second one is obviously the constructor for the feature entry class, just by looking for the name. But IDA did not create a function there. Instead, it just disassembled its code with no function. So one way to tell where IDA failed is to go through your names window, and if you see any C's, this means that you have some code which doesn't belong to any functions. So your automatic analysis, if it works on functions like BinDev does, will not see that code. Here's an example of the VCC sync mode string, which should have been a string like it is on the bottom. But on top is what the auto analysis did. It probably looked at it, and because it saw the push EPX instruction, the heuristic said, if it's push, then it's probably code. So it just started creating code from there, And to a human, it doesn't really look like valid code. Like the ARPL instruction, I've never seen it before in my life. I don't even know what it does. But it's there. And then after that, we actually have 2 bytes, the 64 and 65, which either could even disassemble as real instructions because they're not valid outcodes. So this is obviously an incorrect disassembly. So one of the solutions to this is disable the make final analysis pass. A lot of the data that is disassembled as code happens during the final analysis pass. Because if something is reachable as code from the entry point, then you have a fairly high degree of confidence that it is really code. So before the final analysis pass, all the things that are marked as code are really code. And then all the other things that are marked as data are generally really data. The final analysis pass, when it goes through all the unexplored bytes, it doesn't have any information about, there are no references to these bytes. So it doesn't know if you have a jump to them or a call to them or a data reference. So it just tries to guess based on what the bytes look. And this is how you end up with, this thing being disassembled as code. So if you value accuracy in your disassembly higher than you value completeness or coverage, then you can disable that option. And then all the unexplored bytes will just be leaved as unexplored. So maybe you can later revisit them and manually convert them to whatever they need to be. There are some drawbacks. For example, if you have a B table, which is a sequence of function pointers, when IDA sees the data reference to that B table, it will create the first function pointer there. But since it doesn't know that this is a V table, or it doesn't know how big the V table is, it will not do anything with the other function pointers, so it will leave them as unexplored. And if it doesn't see these function tables, it's not going to see the functions that they point to either. And since there are no direct calls to these functions, it might not even reach that code. So that's not an ideal solution, but it can help if you're really having problems with the data disassembled as code. Another solution which works better if you have symbols is to use the symbol names to tell whether it's code or data, which is what we did in the previous slide. We could look at the constructor function, and from the way it looked, we could tell that it looks like code. So this is what my symbol loading plugin does. When I load the symbols, I actually try to guess whether the symbol refers to a function or some piece of data, and then I create it appropriately. Another thing you can do is you create the data items before functions, because if you haven't created your data byte, it will just be unexplored area in the database. So when IDA creates the function, if the code tracing goes through there, it will just create it as code. And then later, if you try to create data there, it will not work. At least the auto analysis will not do that. You can force it manually, but our goal is to get the auto analysis to do the right thing. So creating the data first ensures that it is really data, and the code tracing algorithm, when it goes through it, it will hit that data and it will stop. It will not convert it back to code. So if you're fairly sure that some piece of information is really data, then you create it first, and then you do your functions. The function chunking problems are, I already talked about the fall through, and the fall through creates that problem where if you have two functions that foo fall throughs to bar, then if foo is analyzed first, then IDA will create a function that covers the entire range of foo and bar. And then later, when it sees a call to bar, it will see, well, this looks like a function, but it's already part of another function, so I'm not going to create it again. And it will just leave it like that. But if bar is analyzed first, you'll get the function bar. And then when foo is analyzed, you'll get the function foo. And IDA can deal with one function jumping to another or falling through to another as long as you create them in the right order. The other problem is this doesn't have to happen with full functions. You can also have function chunks which are interspersed with each other. So I've seen this case where you have a function and then in the middle of it you have the function chunk from some other function. So if foo is created first, you'll get the whole area as one function, and then bar will not be created as a chunk. But if bar is created first, you'll get the chunk in the middle, and then when foo is created, it will be split into two chunks, one before bar, one after. So there's a very simple solution to that, which works amazingly well. You just create the functions backwards, because most of the time the fall through goes down into the database. So if you first create the functions that are on the bottom of the database, and then you start going up creating functions, the functions that are already created sort of act as a boundary for the functions that you're creating now. And this ensures that you don't get one function which contains code from other ones, because you've already created the other ones. So just changing the iteration from going forward to going backwards in my PDB plugin, improved the function chunking very, very significantly. That was really amazing. So now let's look at the code for my plugin, which implements a lot of these things that I talked about. IDA already has a PDB plugin, and that PDB plugin actually comes with a source, which is included in the SDK. If you look at it, it uses the DBG help API, which is the Windows API, because the Windows symbols format, the PDB format, is not documented. So to load these symbols, you have to use the API, so it doesn't work on other platforms. But that's the best we have right now. Its algorithm is very simple. It iterates through all symbols in forward order. For each symbol, it just creates a name in the database, and then it does some very limited guessing based on the symbol name. If the symbol name is string, then it creates a C or a Unicode string. And the string name is what the Microsoft compiler creates for string literals. So if you just have a string literal hard-coded in your source, the symbol for it will be quote, string quote. Then IDA checks, it uses the demangler on the name, since most names in C++ code are mangled. And the demangler tries to guess whether it's code, data, or unknown. So if it's not data, then IDA will create a function there. But this means that if you have something that's unknown, IDA will also create a function there. And this is exactly what happened in the example with a string that was disassembled as data. Because the name there was just a straight name that didn't have that was not mangled. IDA, the demangler couldn't know what it is. So it just returned it's unknown, and then IDA created the function there. Here are the improvements that I've made in my plugin. The first one is I use FPO records to detect functions. FPO records stands for frame pointer emission record. For functions that don't have a base pointer, it's very hard to get a stack backtrace in a debugger. So normally, if you don't have this information in the debugger, you'll just hit the function that doesn't have a base pointer, and that's the end of your stack trace. So that's why the compiler creates these FPO records in the debugging symbols, which tell you how big the stack frame is for every function that doesn't have a stack pointer. So if when processing the PDB file, if I see this FPO record, I know this is definitely a function. So I create this function. Then I also do heuristics based on names. Unlike IDA, if the demangled name is of type unknown, then I'm not going to create a function there. Because in my experience, this gives better results. I also have special handling for imports, floats, doubles, GUIDs, better detection of the string type, whether it's ASCII or Unicode. I have special handling of V tables, and also I apply the symbols in multiple passes, which I'll go over on the next slide, which increases the accuracy of the analysis. And I also have a GUI, which the original plugin doesn't have. It's available under a BSD license from this website, and I'm releasing version 0.04 today, which has some improvements over the previous versions. So here are the symbol types here's how I guess what the type of a certain symbol is, mostly based on the names. All the imports start with __in. So from that I guess that the symbol is an import. Floats and doubles start with __real, and then I can tell whether it's a float or a double based on how many digits it has after that. Strings have a distinctive name too. GUIDs, which are used to refer to COM objects, also start. There is a list of maybe a dozen common prefixes for them, and if you see a variable that has that prefix, it is most likely a GUID. And GUIDs are just 16-byte data items. V tables all contain V table in their name, so you can detect them this way. Functions would either have an FPO record, or the demangler will say it's code. Then I have data items, which the demangler recognizes as data, and then I have unknown, which is everything that I didn't recognize. So when I apply the symbols, I have 4 passes. In the first pass, I rename all existing names. So I go through all the symbols, and I check if there's already a name for that symbol in the database. If there is, I rename it. This avoids naming collisions in the second pass, where I go through and I set all the names in the database. I just set the names, I don't actually create anything there, so the bytes are still left unexplored. The reason to have the names there first is when I actually create the data items in the third pass, I check if I'm creating a GUID, it needs 16 bytes. So I'm going to check are there 16 bytes available before I hit the next symbol name. Because if there's a symbol name 4 bytes in, then my detection algorithm got it wrong. It's not really a GUID. You're not going to have a symbol name in the middle of the data item. Once all the data items are created in the database, I go ahead and I create the functions. And the data items act as sort of boundaries for the functions. So the functions will nicely be split into chunks around the data items instead of including them in their bodies, which gives better results. So let me show you what the plugin does. Now normally you don't run the plugin after the database is already disassembled. Normally you would, when you load the file initially, the plugin will kick in and do it. And it's actually better to do the plugin when you load the database the first time, because the database is empty and the plugin can do its best work. But you can also run it after the fact, which I'm going to do now. So when you run the plugin, it starts, then it tells you whether it got the PDB symbols, it gives you a count to the file. And then here's a list of, here's the GUI that you get. You get a list of functions. You have a list of symbols, and for each symbol you have the type. And like to sort them by types. So you have, here's the different types. These things are recognized as data based on what the DMAG will return. Scroll down. Here we have some functions. Then after that, we'll have functions with FPO records. And the difference between those is that for the FPO records, we're 100% sure. For the other functions, we're mostly sure. After that, we have some GUIDs. You can see that all the GUIDs start with _IID or _CLSID. Then we have imports. Then we have strings. And then we have unknown. and V tables at the end. And the V table actually tells you which class it is for, and it tells you that it's a V table. So if I say OK, if you say cancel, then it just aborts. If you say OK, then the 4 passes run, and all the names are applied. So let's wrap it up. Any questions? Yes?
Why don't you put the VF table as V table symbols? When you look up the name for checking the symbol product,
Yes.
why don't you check for VF table as well?
I do. In the So if you look at the so here I check for VF table and I recognize that this symbol is a V table. Okay. Anybody else? All right. Thank you.